What if I told you there was a single, evidence-based story that could explain, well, everything from the Big Bang to the global economy, and maybe even give us a new way to cure cancer? Okay, let's dive into this because that is the huge, radical idea behind what's called cosmic evolution. The scientist behind all this, Eric Chaisson, he kicks things off with these bold, almost philosophical statements. He says he believes evolution acts on all complex systems, not just living things. He believes that energy, more than anything else, is what drives complexity. But then, just as you're settling in, he completely pulls the rug out. He says, actually, I believe none of these things. See, as a scientist, he doesn't believe, he reasons. These aren't just articles of faith for him. They're testable ideas about how the universe actually works. And that little twist sets the stage for a completely evidence-based journey. So what exactly is this story he's reasoning about? It's the idea that for the first time, modern science can trace a single, unbroken thread of change all the way through time. It's this grand narrative that connects the dots, from primal energy evolving into particles, those particles into atoms, atoms into galaxies and stars, and eventually right here to the technological civilization we're all a part of today. And this is it, the cosmic arrow of time. It maps out these major phases where brand new, more complex systems just appeared. You can see it right here. Particulate evolution gives way to galaxies, then you get stars, planets, life, and boom, finally, cultural evolution. It's just this incredible sequence of increasing order and complexity, all unfolding over billions and billions of years. Okay, but hold on. This leads to a gigantic question, right? A central paradox in physics. If the entire universe is supposed to be getting more disorderly and chaotic over time, how in the world do you explain, well, us? How does all of this amazing, intricate order just emerge from chaos? I mean, think about it. On one hand, you have this second law of thermodynamics. It's one of the most fundamental rules of the cosmos, and it basically says that, on the whole, disorder, what scientists call entropy, always increases. Things fall apart. But then you just look around and you see the complete opposite. You see galaxies, stars, life, society, all these stunning examples of order and incredible complexity. So what gives? Well, the answer isn't that the second law is wrong. Not at all. The answer, the secret, lies in energy. Specifically, it's about the way energy flows through what are called open systems, things like a star, a plant, or even a city. That flow of energy, that's the engine that literally builds complexity. And to measure this, Chaisson came up with this brilliant key metric he calls energy rate density. The easiest way to think about it is as a complexity score for any system. It's just the amount of energy flowing through something per chunk of its mass per second. That's it. And this is where it gets really mind-blowing. When you start applying this metric to things, the stunning pattern just emerges from the noise. The Milky Way galaxy, tiny energy rate density. The sun is a bit higher. Our planet Earth, a little higher still. But then look at the jump when life appears. Plants, and then animals. And then, the biggest of all, modern human society. It's undeniable. As systems get more complex, their energy rate density consistently and dramatically shoots up. And to really get a sense of the scale we're talking about, check this out. The energy rate density of your brain, right now, is about 100,000 times greater than the energy rate density of the sun. By this measure, you and I are vastly more complex energy processing systems than a literal star. Okay, so it's a really cool cosmic theory, for sure. But here's where it stops being about astronomy and starts getting incredibly practical. This single metric, this way of seeing the world through the lens of energy flow, can be applied to some of our most urgent human-scale problems. Take economics. We can actually measure the energy rate density of entire cities. A rising score, like we see in Shanghai, suggests a booming, vibrant economy. A stable one, like Toronto, points to a kind of dynamic stability. And a falling score, like what's been seen in Washington, could be a real objective red flag for economic decline. This energy flow is like a vital sign for a city's health. This framework also gives us a totally fresh perspective on climate change. For just a second, forget about greenhouse gases. The second law of thermodynamics itself tells us that every single joule of energy we use from non-renewable sources, coal, oil, you name it, ultimately ends up as waste heat, which directly warms our planet. It is an unavoidable physical consequence. And that logic leads to a really powerful, almost inescapable conclusion.
If our complex society needs more and more energy to survive, and it does, the only sustainable long-term way to get it without literally cooking ourselves is solar. Why? Because the sun's energy is already part of Earth's natural heat budget. Tapping into it doesn't add new heat to the system. From a purely thermodynamic point of view, it's the only real solution.
So let's look to the future for a second. The next big phase of this cultural evolution is pretty clearly the human-machine interface. But there's a huge difference here. Our biological evolution is incredibly slow, measured in thousands of years. But the evolution of our technology, our machines, that's happening at a blistering, accelerating pace. And guess what? Our machines follow the exact same trend of rising energy rate density. From the old room-sized ENIAC computer to today's supercomputers, that complexity score has been climbing steadily. As our computers have gotten smaller and more powerful, their energy rate density has shot up, and it's now rivaling and even exceeding that of human society itself. All right, so we've journeyed from the cosmos to cities to computers. But here is, by far, the most surprising application. Can this cosmic way of thinking actually help us cure cancer? From this new perspective, cancer isn't just a biological disease. It's a systems disease of dysregulated energy. A healthy cell is a masterpiece operating in a perfect, optimal range of energy rate density. A cancer cell, surprisingly, is actually less complex. Now, it uses a ton of energy, yeah, but its mass grows even faster, which causes its overall complexity score to drop below that healthy range. It becomes, in a very real sense, more disordered. Now, reframing the problem like this suggests a totally radical new strategy. Our current treatments try to destroy cancer cells. We either blast them with too much energy, like radiation, or starve them with too little, like chemo. But what if, instead of killing the cell, we try to cure it? The idea here is to find a way to gently push its energy rate density back up into that healthy range, essentially reverting the cancerous cell back to normal function. So, let's take a breath. After this incredible journey, from galaxies all the way down to genes, what are the big takeaways? What does this all really mean for how we see our world? Well, Chaisson boils it down to 4 main points. First, that cosmic evolution offers this grand synthesis, a way to unify all the sciences under one big story. Second, the expansion of the universe itself is what creates the conditions for complexity to arise in the first place. Third, this idea of energy rate density acts like a common currency across all of nature to measure that complexity. And finally, that evolution isn't just for biology, it's a universal process with really deep lessons for our own society. And this really is the principle of cosmic selection in a nutshell. It's not just about survival of the fittest. It's about the survival of systems, living or not, that can best manage their flow of energy. The ones that use optimal amounts of energy thrive. And the ones that don't, well, they disappear. But ultimately, the real point is that this is so much more than just an abstract theory for physicists. It's a practical tool. It's a new lens for understanding our economy, our technology, our health, and the huge choices we all need to make to build a sustainable future. Which leaves us with one final and pretty vital question. If the ability to optimally manage energy flow is the single defining characteristic of all successful systems throughout the entire history of the cosmos, how wisely are we as a global civilization managing ours?